In the second part of this lecture, we'll talk about several advanced topics in computer architecture that are covered in much greater detail in 429, but I think it's important that we discuss them in 229 so that we understand how actual processors work and how the design, the basic design that we learn in 229 is adapted for these actual processors. So one of the concepts is the concept of speculation. For example, for control speculation, we are guessing what to do with an instruction, and we'll try to start the operations as soon as possible. We'll check whether the guess was right, and we'll complete the operation. If not, we're going to roll back. And this is common both for static and dynamic multiple issues. So the examples that we want to talk in this part of the lecture are the speculation on a branch outcome and the speculation on a load. So for speculation on a branch outcome, we need to consider that giving a branch, there are two possible paths of execution. In this picture, I illustrate in the red path and the blue path. When we do the branch prediction, we try to do the best guess that we can for which path should be followed, and we start fetching instructions from that path. Notice there's three dots here. You'll say that there might be many instructions in that block, so I'm going to start fetching and executing instruction from that block. But if the path that I should have followed is different, then what I'm going to do, I'm going to flush all these instructions from the pipeline using the technique that we learned in the first half of this lecture, and then start fetching from the other half. That will be the new value of the PC that I will introduce. So if it was an exception, the value of the PC that I would introduce was the value of the exception handler. If the problem was an speculation that went wrong, the value of the PC that I'm going to introduce into the PC is the correct value of the PC to execute the right path. Another type of speculation is data speculation that occurs when I have a load and I may have potential stores in the code. So consider this piece of code here where there is a load that occurs, there is a store that occurs, there is a load that occurs here. And assume that I do not know whether the value of T1 and the value of S3 are the same. If the value of T1 and S3 are not the same, I can safely perform this load before this store because I'm loading from a different memory location. However, if the value of S3 and T1 are the same, I cannot do that because the value that this load should be loading is the value stored by that store in that case. So speculation consists on I do the load before the store, so I assuming that the S3 and T1 are not the same, and if they happen to be the same, then I have to repeat the load. So if the store was to the same memory location as the load, the processor is going to have to issue the load again. So this can be done in a number of different ways. I may have a compiler reordering the instructions, for example, move the load before a branch or moving the load before a store, and then include a fix-up instruction. So in this case, this is the moving the load before the store case, but I could also be moving the load before a branch in the case of a control flow dependence. So here I move the load before the store, and what I'm guessing here is that S3 is not the same as T1. So after this store, then I check to see whether T1 and S3 are not the same. If they are not the same, then I'm going to skip this fix up, and I'm going to go down here. If they are the same, I have to repeat the load before I can, and then in this case I have to repeat the add also because they add depend on the load. So this is something that a compiler can do with any instruction set architecture. In some instruction set architectures, such as in the Itanium, there were special instructions to speculate that way. So so here I speculate that the load store are to different locations, and I redo the load if the load is incorrect. So one thing that I need to be aware here is that this load could, for example, cause an exception, especially if I'm speculating a load before a branch. The branch could be to test, for example, whether this value is 0, and now I'm loading from the address 0, which will produce a segmentation fault. I could be producing an incorrect code that was correct before my compiler became smart and tried to do the optimization. So in some architectures, I have instructions that are special instructions for speculation that will not gonna cause deceptions, so that I do not have that problem. I can do hardware speculation, so the hardware can look ahead for instructions to execute and can buffer the results until it determines that they are needed. Then it can flush buffers when there is incorrect speculation. And the other thing I just mentioned is the problem with speculation and deception. What if I have an exception that occurs because I am executing an instruction speculative, an instruction that should never have been executed in the correct execution of the program? So, for example, I do a speculative load before a null pointer check. So there was a branch that was checking whether a pointer was null. After that branch, there was a load. I decide that I'm going to do the load before the branch, speculating that the address is correct. In the case of static speculation, I could add instruction set architecture support to defer the exceptions. So I could, for example, have a special load instruction that I tell in the hardware, this is a speculative load. Do not produce an exception. If this leads to an exception, simply ignore the load. I'm going to do that again when it's safe. In the case of dynamic speculation, I can buffer the exceptions until the instruction completion, which may never occur. So remember the idea that I said that in the pipeline, if an exception, if an instruction is causing an exception, the instruction raises a flag and says, I am an accepting causing instruction. Every instruction before me will be null. I'll be null itself, but I go to the end of the pipeline. Well, if that instruction happens to be executing speculatively, it may happen that the instruction actually never gets to the end of the pipeline, and therefore the exception is never raised. So that will be one way to deal with the issue. Another way is there are architectures that are called out-of-order execution architecture, where the instructions can be executed but not committed. They remain in something called a reorder buffer, waiting for commitment, and they will only commit if they are in the correct path of execution. So in static multiple issues, I will have the compiler grouping the instructions into issue packets, and a group of instructions that can be issued on a single cycle will be in the same packet and will be determined by the pipeline resources required. We can think of an issue packet generated by these compilers as a very long instruction, and therefore the architectures that allow that, not every processor allows that. The processors that are designed to allow that are called VLIW, or very long instruction word processors. So it will going to specify multiple concurrent operations to be executed in the same processor, and thus the name VLIW. We also need to discuss the dynamic pipeline scheduling that occurs in processors. So I wanted to allow the processor to execute instructions out of order to avoid stalls, because some instructions may take longer than others, and other instructions may have their operands already available, therefore their execution can proceed. But the committing of the results must be in order. So, for example, if I have a load that writes to the register 31, and then I have an add that uses the value of 31, and then it follows by a sub and an AND I can start the sub while the add is waiting for the load. Remember that the add will not going to be able to proceed because the load takes time to bring the data from the memory. But the sub is not depending on anything, so I could start the sub before the add, and I could even complete the sub before the add is executed. But I will have to wait to commit the value of the sub because the instructions have to commit in order. One of the reasons that they have to commit in order is for debugging. When debugging, I wanted to see the effect of the instructions in the order in which they occur. So here is a design that gives you an overview of how such processors are designed. So there is an instruction fetch and decoding unit on the top, and then I have reservation stations. So I fetch and decode the units, and I have different functional units here. Some instructions may be load store instructions, some instructions may be integer instructions, some instructions may be floating point instructions. By going through this reservation station, so I send each instruction to the reservation station in front of the correct functional unit, and the instructions will sit there until their operands are available. When their operands become available, they can be sent to the corresponding functional units to be executed, and once they are executed, they go to this committee unit. This committee unit is often called a reorder buffer, and they sit there until every instruction in front of them have completed. So the execution happens out of order. And also I obtain values from these instructions. I can send these values back to the reservation station so that the operands for the instructions that are sitting in the reservation stations are now available. So it's an out of order issue that it's an in order issue, so it will preserve the dependence. It can hold depending operations, and the results also are sent to the waiting reservation station so that more instructions can be executed. And in the end, I have an in-order commit that is, I can supply the operands for the issued instructions. So this is a very high-level discussion of this process. We have these reorder buffers for the register writes that are in the committee unit. Again, we discussed these designs in much more detail in 429. And then we have another thing that happens is that there is register renaming in the hardware. So the registers that you specify in your assembly program are not necessarily actually the registers that are used when you execute the instructions. The reservation stations and the reorder buffer provide register renaming. So if I have a value that is in a register that I still need, and now I write another value to the same register, what the hardware going to do is create a new register for the second one, so there is no conflict with the first one, and I can execute both instructions in parallel. So when you issue an instruction to the reservation station, if the operand is available in the register file or in the reorder buffer, you can copy that value into the reservation station, and then you no longer require it in the register, and you can overwrite the value that was in the register. If the operand is not available when you are waiting the reservation station, you are provided with the name of the register that you're going to need. So this is it will be provided to the reservation station by a function unit. So the reservation station is told when the value of register 17 is broadcast by any reservation unit, that's the value that you need. So the register update may not even be required. So one of the lessons from here is that the simple model that we studied throughout 229 until now, that the registers are these monolithic places where we put data. In the actual execution of the program, in modern processors, that's not the case. There is the register renaming. Again, we study register renaming in much more detail in 429. For speculation, we predicted a branch, the value of a branch, and you continue executing, but we do not commit the results until the branch outcome is known. So even though I go ahead and I fetch, I put the instruction in front of the reservation stations. If the operands are available, I issue the instruction, I execute them, I obtain the result. I do not write the value into the registers until I know that the instruction should have been executed. In the case of load speculation, I'm going to avoid the load and the cache miss delays. We haven't discussed cache yet. It's our next unit, but we're going to understand that there can be significant delays to bring data from the memory. And the idea of load speculation is to avoid those delays. So I can predict, for example, whether the address that the load will gonna go without knowing the actual address, or I can predict the value of the load, or I can load before completing an outstanding store, or I can bypass stored values to the load unit. In any one of those cases, when I'm speculating on a load, I do any one of those techniques to improve the performance of the load instructions, but I can never commit the value to the register until I find that the load is no longer speculative. I find that the load has the correct address, that there was no store that wrote to the same location, etc. So that's the way I handle speculation. And one of the questions is, why do we do dynamic scheduling? Why do we have the hardware reordering the order of instruction of the execution of the instructions? Why not execute instructions in the order that they appear in the assembly program or generated by either a programmer or by the compiler? So why not just let the compiler schedule the code? The first thing is that not all stalls are predictable, so it may be hard for the compiler to have a full picture of actually which data is available when during the execution of the program. For example, we may have cache misses that may produce different delays. And the other thing is that it may be difficult to do scheduling around branches all the time, and the branch outcome is dynamically determined. Sometimes even the target of the branch is dynamically determined if the branch is on a register-based branch, for example. And you have different implementations of an instruction set architecture that may have different latencies and different hazards. So it can become very difficult for a compiler to statically generate the best scheduling for a program. And that's why we end up with what is called out-of-order execution architectures, where the scheduling is dynamic. So does multiple issue work? Does it work for us to try to execute multiple instructions at the same time in these superscalar machines that have multiple issue pipelines? Yes, but not as much as would like to think that they did. There was a time that people thought that we would keep increasing the number of issues in the pipeline, and that would go to 8 or 16 instructions being issued at each cycle. It turns out that programs have data dependencies and control dependencies, and those dependencies limit the number of instructions that they can issue at the same time. So the real dependency in the program limited the instruction-level parallelism. There are some dependencies that are very hard to eliminate. Some dependencies are natural dependencies that are originated by the algorithm that you are executing. There are problems with pointer aliases, for example, to determine that a load and a store do not go to the same memory location can be difficult statically. Some parallelisms can be harder to expose. For example, you may have a limited window size that you can look into the instruction stream to decide which instructions can be issued at a given time. There are memory delays that can limit what you can do, because it takes time for the data to come from the memory, and there is also limited bandwidth to the memory. So you may be limited by the amount of data that you can bring from the memory or put to the memory on average per cycle. So it can be hard to keep many pipelines full because you simply don't have enough throughput of data to bring to these pipelines. And speculation can help if it's done well. So these high-level concepts, I think, are very important for us to understand how processors actually work. And as I said, they'll be covered in much more detail in 429.